Ed Carlson was a farmer who, like so many others, had lost nearly all his cattle to a mysterious death. He was on a 200-mile journey driving through the blizzard in search of an answer that no one else dared to look for. And all he carried with him was a jug of blood, a dead cow, and a flicker of hope. Why was he the only one searching for answers? And why were the cows dying? Little did he know that this journey would lead to one of the most fascinating discoveries in science. At the Ontario Veterinary College, Frank William Schofield, who was the director of veterinary hygiene and research, took notice of an outbreak that caused cattle to bleed silently and die. Naturally, the first suspect was an infection, and since seemingly healthy cattle were also affected, the disease was assumed to be communicable. To confirm this, he conducted tests on flesh of the dead animals, which showed no signs of infection, which are usually heat and swelling. And that's when he began to suspect that this wasn't a disease in the usual sense. It wasn't bacterial, it wasn't communicable. Something else was going on. But there was one detail that stood out. Most of the animals died in their sleep, some just after feeding and others following simple procedures like dehorning. He conducted an extensive autopsy and found that even though the animals bled to death, there was very little blood that was lost. And all this pointed to just one thing: something was poisoning the blood. And the most likely suspect was the feed. So Schofield conducted a careful study of the diet. The animals that died had all been fed sweet clover. Sweet clover was widely used. It was common, reliable, and nutritious. It had been fed to cattle for years without any issue. So he asked himself three questions, three possibilities that would determine the truth. Is sweet clover injurious because of a poisonous principle in the plant? This could not be possible, since sweet clover is the usual silage that had been fed for a very long time. And a lot of farmers grew it, and only a few of their cattle had the disease. Is sweet clover injurious because of a deficiency in some food element? And this was also not possible, since studies conducted on the plant found it to be rich in nitrogen and protein, and well balanced, and was also an excellent cost nutrition option. And the final question was, is sweet clover injurious because of a poisonous product formed in it by microorganisms? And this was the turning point. The disease only appeared in cattle fed moldy batches of sweet clover silage. He realized that the mold wasn't just spoiling the plant, it was likely releasing a toxin or altering a chemical already present in the plant into something far more dangerous. And that's when he proposed a new disease and called it sweet clover disease. And his advice was direct: do not feed moldy sweet clover. Even if it looks fine and even if you're unsure, do not risk it. This warning spread through southern Ontario, and for a time, cattle were saved. But this was 1920 in Canada. There were no national alerts, no veterinary bulletins crossing borders. And in farms hundreds of miles away, the bleeding would continue for years. It was the middle of the Great Depression. Unemployment affecting close to 30% of the population, 9,000 banks shut, causing widespread bank runs. Farmers faced a worse outlook. One-third had lost their land, declining crop prices and drought crippled their finances. And adding to the worst condition was a blizzard like never before. Ed Carlson was a farmer in Wisconsin, and like most others at that time, he was struggling, hit hard both by the economy and the weather. And buying expensive cattle feed was out of the question. So like many farmers, he turned to the only option that made sense: sweet clover silage. But something wasn't right this time. In just 2 months, he had already lost 5 cows. And if this kept up, he knew that it wasn't just his herd that was at risk, it was the whole farm. He spoke to a local veterinarian who, upon identifying it as sweet clover disease, suggested switching to a different feed. But Carlson dismissed it and wasn't an ardent believer in usual signs. He had fed sweet clover all his life. His father had and his grandfather too. But there was no problem before, so why now? What Carlson didn't know and the vet didn't fully understand either was that this time the sweet clover had mold in it. The moisture, the weather, and the way it had been stored had changed. He lost more of his stock and now he had to act fast or lose everything. All that he had was one last try. He took a milk jug, filled it with blood from one of his dead cows, loaded the carcass into the back of his truck, and set off for a journey of 200 miles through snow and wind. He was on his way to the state capital, Madison, to the agriculture experiment station where he'd find the office of the state veterinarian. When he arrived at the University of Wisconsin, the office was closed, and Carlson needed an answer that day. He started going around the campus door to door looking for anyone who might listen. And that's when it happened. He walked through one of those doors, and what waited for him on the other side would set off a chain of events that would change the world forever. Inside the biochemistry building that Carlson stepped into, purely out of desperation, was a man named Carl Link. At that time, Link was an associate professor of agriculture chemistry. His main area of focus wasn't animal disease or blood disorders, it was plant carbohydrates. Carlson laid all that he had brought with him, the jug of blood, the carcass, and the 100 pounds of sweet clover in front of Link, and explained what had happened and asked for help. And strangely enough, Link recognized the problem almost immediately. A year earlier in 1932, Link had learned about the strange bleeding disease in cattle from Ross A. Gartner, who was then heading the biochemistry department at the University of Minnesota. Link himself had been planning to study a compound in sweet clover called coumarin, a benzopyrone class of molecule with the formula C9H6O2. That is what gives the sweet clover its sweet smell and bitter aftertaste and serves as a deterrent against predators. But Link hadn't begun his studies. And now the problem was right in front of him, and the best solution he could offer at that point was what he knew from previous work, particularly the findings of M. Roderick, a veterinarian who had picked up where Schofield left off. Roderick had done coagulation studies and discovered that these cattle were bleeding to death because of their prothrombin levels, which were dangerously low, and he called it plasma prothrombin defect. Prothrombin is a protein that is responsible for blood coagulation. It sits right near the end of the coagulation cascade. It gets converted into thrombin, which then turns into fibrinogen into fibrin, which are long, sticky strands that form the structure of a blood clot. These fibrin strands get cross-linked to create a stable mesh, sealing the wound. This gave Link an idea to begin to understand what was happening in the disease, but there was no solution at the moment. Link told Carlson to stop feeding the moldy hay immediately, and for any cows that were still alive but showing symptoms, he recommended blood transfusion to try and save them. And without a solution, Carlson left back home. In the lab with Link was E.W. Schoffel, a German agriculture chemist who had been working with him since 1929. When he saw Ed Carlson leave with nothing more than a suggestion to stop using moldy hay and try transfusion, he became a bit furious. Schoffel dipped his hand into the jug of blood. It was freezing outside, well below zero, but the blood didn't show any signs of clotting. Eventually, Link had to head home, and that's when Schoffel said, "There's a destiny that shapes our ends." Schoffel stayed back and told him he'd pull some notes and have few things ready by Monday morning. They didn't have much to go on. No formulas, no structure, and not even a clear idea of what they were looking for, except that somewhere in the sweet clover was a compound that made animals bleed. And that was it. They had to go in blind. The process was slow, full of failed experiments, dead ends, and repeated mistakes. As they later wrote in their own words, no useful purpose would be served by listing in detail the numerous and diverse unsuccessful trials which finally led to the fractionation. Schoffel started with the basics, simple extraction test using alcohol. But since they didn't know what the molecule looked like, they couldn't exactly track it under a microscope or measure it on a scale. So there was no easy way to tell if any of the byproducts contained the hemorrhagic agent. And if it was there, how would they even know? The only option they had was to test the extracts on live rabbits and see if it messed with their blood's ability to clot. That's where bioassay came in. Since the compound they were trying to find was known to cause bleeding, and specifically lower prothrombin levels, and as a result increase clotting time, the goal was to measure just that. They first collected blood from the rabbit before feeding and extracted the plasma. This is called the pre-feed plasma, and it was stored at 0 degrees Celsius to keep it stable. Then, they fasted the rabbit and fed it the test material and waited for 20 to 40 hours. After that, they took a second blood sample. This was called the pathic plasma, and it was expected to clot more slowly if the extract had done something. And to test the clotting time, they used Quick's method, where calcium and thromboplastin are added into the plasma and the time it takes to clot is timed, mimicking the process in vitro. Thromboplastin acts on factor 10, helping to activate it, then converts prothrombin into thrombin, and then thrombin goes on to convert fibrinogen to fibrin. Calcium essentially acts as a cofactor for thromboplastin and prothrombin. Finally, the pre-feed plasma was diluted step by step until its clotting time matched the pathic plasma. Then they calculated a ratio. The index was equal to pre-feed plasma concentration divided by pathic plasma concentration. If the ratio was 1, that meant there was no change and the rabbit's blood still clotted normally. If the ratio was less than 1, it meant clotting was slower and the extract had the hemorrhagic agent. If the ratio was way below 1, like 0.1 or 0.05, that meant that the extract had a strong anticoagulant effect and they were isolating something powerful. And then they made one more important observation. The rabbits did not develop immunity to the hemorrhagic agent, which meant that after giving them time to recover, they could be used again. There were no lives lost, no need to sacrifice the animal for every test. They finally had a compass, a way to track something they still couldn't see, but now could follow step by step. And with that, the real work of extracting the hemorrhagic compound could finally begin. The breakthrough in the extraction process came from another chemist in Link's lab, Harold A. Campbell. Campbell picked up the work where Schoffel left, and from 1934 to 1939, he stuck with it, repeating a 16-step extraction process over and over. At every step, he'd use the bioassay to test whether the hemorrhagic agent was still present. If it wasn't, he'd start over from scratch. This wasn't a quick process. It was slow, methodical, and full of repetition. At the end of the 9 steps were just 6 milligrams of a sticky green substance which they called green gunk. It was free from fats, waxes, amines, water-soluble acid, and water-soluble chlorophyll breakdown product. Yet, the chemical nature was still unknown. That tiny amount reduced prothrombin levels in the rabbits to 10% of the normal within 48 hours. And that was equal to 75 milligrams of the sweet clover. With this green gunk, which had the agent in high concentration, the remaining 7 steps were performed with the same bioassay. And finally, on June 28, 1939, everything changed. Campbell had isolated a crystalline substance that had the same reduction in prothrombin as 50 grams of the spoiled hay sample. And for the first time, he had the empirical formula of the hemorrhagic agent, which was C19H12O6. Now, with the formula in hand, they could finally identify the full structure, isolate the pure compound, and give it a name. And the final phase of the work was taken up by 2 other chemists in Link's lab, Mark Stammen and Charles Hubner. They were responsible for identifying the exact structure of the compound and eventually synthesizing it. Through a series of degradation reactions, on April 1, 1940, they figured out that it belonged to the 4-hydroxycoumarin class. That meant that the core of the molecule was a coumarin ring with a hydroxyl group attached to the 4th carbon of the lactone ring. But what made this unique was this compound was made up of 2 4-hydroxycoumarin molecules and they were linked together by a methylene bridge at the 3rd position. And now they finally understood how it formed. When the hay sat in the right conditions with moisture, the mold stepped in. First, the coumarin got oxidized into 4-hydroxycoumarin, and then, in presence of formaldehyde, a byproduct of the mold, 2 of these hydroxycoumarin molecules were linked together. And that's how dicumarol was born. Under normal conditions for the blood to clot, it relies on a group of proteins called clotting factors, specifically factors 2, 7, 9, and 10. These are known as vitamin K dependent clotting factors. Each of these factors has a glutamate residue that needs to be modified through gamma carboxylation to become sticky. That stickiness helps them to attach to surfaces, which is essential for forming a proper clot and initiating the cascade. The carboxylation process needs vitamin K as a cofactor. Vitamin K cycles between its reduced form and oxidized form through a continuous redox cycle. Now here's where dicumarol steps in. It competitively binds to vitamin K epoxide reductase, the enzyme responsible for converting KO back to KH2. This blockage stalls the vitamin K cycle, and if vitamin K can't be recycled, the carboxylation stops. The clotting factors never get fully activated. At first, this means that the blood takes longer to clot, but eventually, as all the clotting factors get used up and not replaced, the blood stops clotting. With the compound now isolated and synthesized, Link was eager to take it further, to see if dicumarol could be used in human medicine. Between 1940 and 1942, he wrote to several hospitals and directors, including the Mayo Clinic and Wisconsin General Hospital, describing the dicumarol's effects on blood clotting and its possible use as an anticoagulant. He explained that since it worked by interfering with vitamin K metabolism, its effect could be reversed with high doses of vitamin K, making it controllable. But most of the clinicians were hesitant. Back then, vitamin K's role wasn't fully understood, and there were concerns about its toxicity, especially in high doses. So one by one, they turned Link down. Dr. Shepard Shapiro, a clinician in New York City, was the first to see its potential. He not only agreed to try dicumarol in clinical settings, but also confirmed that high doses of vitamin K could successfully reverse its anticoagulant effects, proving it could be used safely. Between 1941 and 1944, nearly 50 clinical studies were published on dicumarol. It became a serious alternative to heparin, the popular anticoagulant at that time. But dicumarol had a problem. It worked slowly and its effects were hard to predict. Some patients needed higher doses, and at those levels, the risk of internal bleeding went up, sometimes dangerously. It wasn't perfect, hence, it was always used with caution. After its introduction into clinical use, Link took a break. It was 1945 and he was worn out from years of lab work and decided to go on vacation. But during the trip, he was caught in a cold rainstorm, which triggered a relapse of his tuberculosis, something he had dealt with years earlier. He was admitted to Lakeview Sanatorium and ordered to rest for at least 6 months. Stuck in recovery with nothing to do, Link began reading his lab notebooks. And while flipping through papers and browsing medical journals, something caught his attention. An article on uncontrolled rodent infestation across American cities and farms, causing millions of dollars in damage every year. He began reading more about the history of rodent control all the way from ancient times. When Link returned to his lab, he couldn't stop thinking about it. The potential of dicumarol not just as a drug but as a rodenticide. He began testing it along with his colleagues. But there was a problem. Rats feed on grains and greens, all naturally rich in vitamin K. And because dicumarol has a slow onset, the vitamin K in the diet would often neutralize its effect before it could cause harm. But by that time, Link's lab had already synthesized over 100 related compounds while studying dicumarol. One of them, a compound labeled number 42, stood out. It was far more potent than dicumarol and it produced a uniform drop in prothrombin levels. And most importantly, rats didn't avoid it, which they called bait shyness. This compound was patented by the Wisconsin Alumni Research Foundation and named warfarin, a combination of warf for the foundation and arin from coumarin. Warfarin, another molecule in the 4-hydroxycoumarin class, shares the same basic ring structure, a 4-hydroxycoumarin core. But unlike dicumarol, which is a dimer made of two identical rings, warfarin has a single ring with a side chain attached to the third carbon. This side chain includes a ketone and a phenyl group, a structure that's bulky but also flexible. And that flexibility makes a difference. It allows warfarin to fit better inside the active site of VKOR, the enzyme it is designed to block, leading to a stronger binding, more reliable inhibition and overall greater potency than dicumarol. Link's discovery was licensed to a businessman named Lee Ratner, who founded a company to manufacture and distribute it. He called it Decon, short for decontaminate, and it revolutionized rodent control, generating around $100,000 per week in revenue. Within a few years, warfarin became the most effective and widely adopted rodenticide in history. It was among the safest and also highly lethal in rodents, with very few reported human fatalities. By the early 1950s, over 140 million pounds of warfarin had been manufactured. And in 1956, Lee Ratner, the man who turned warfarin into a commercial success, sold Decon for $7 million. The major turning point in this 2.5-decade journey came with an unexpected event, one that would go on to save millions of human lives every year, even to this day. A 22-year-old Army inductee, EJH, had become depressed after being drafted into military service. He had read about Decon, the new rat poison that was making headlines, and knew that its active ingredient warfarin was lethal to rodents. He bought a box of the product which contained 567 milligrams of warfarin mixed with cornstarch. But the next morning, nothing had changed. So he kept taking the same amount daily for the next 5 days, until he had consumed the entire carton. On the final day, he began to feel discomfort and bleeding from his nostrils. He regretted his choice and rushed to the US Naval Hospital in Philadelphia on April 4, 1951. He was hospitalized and treated with vitamin K, the antidote to warfarin, along with fresh whole blood. For several days, there was little improvement, but by April 9th, his condition finally began to reverse. Over the next 3 days, EJH had a full recovery with no permanent damage. This incident confirmed something crucial. Warfarin wasn't acutely toxic to humans. It required repeated dosing over a period of time to take effect, making intentional or accidental overdose less likely to be fatal, especially under medical care. It also proved that warfarin was more potent than dicumarol, and most importantly, its effect could be reversed with vitamin K. Together, these insights cleared the path for warfarin's entry into clinical medicine as a life-saving anticoagulant. And Link, through his friend SM Gordon of Endo Labs, made it available for clinical use under the name Coumadin Sodium. Warfarin today treats conditions where early intervention can mean the difference between life and death, saving around 1 million lives a year. And the journey to this point? It wasn't fast and it wasn't clean. It took nearly 25 years. It started with the desperation of a farmer who chose to search for answers, while others simply tried feeding cleaner hay. It took the empathy of a scientist who was disturbed when the same farmer had to leave without an answer. It took the commitment of dozens of researchers who picked up the trail, repeating failed experiments and slowly closing in on the truth. They didn't do it for fame, they did it because someone had to, and without their obsession, we might never have discovered what became one of the most important drugs in medical history. Dr. Frank W. Schofield, who first documented the strange bleeding disease in cattle and called it sweet clover disease, was rushed to a hospital after suffering a heart attack. And the drug that saved his life was warfarin.